Welcome to episode 122 of your CYSA Plus Prepcast. In this episode, we turn our focus to secure coding, an essential discipline not only for developers but also for cybersecurity analysts. While writing secure code is traditionally viewed as a software engineering function, security professionals play a critical role in reviewing, evaluating, and enforcing secure coding practices across the development lifecycle. Understanding how insecure code creates attack vectors and how to prevent these through rigorous secure coding techniques is vital for vulnerability management, penetration testing, code reviews, and incident response. These practices are foundational for maintaining application security and are directly aligned with your preparation for the CYSA Plus exam. Let's begin with a definition. Secure coding is the practice of designing, writing, and maintaining code with security in mind. It involves applying principles, patterns, and controls that reduce the likelihood of introducing exploitable vulnerabilities into software applications. These principles extend beyond writing syntax. They require an understanding of threat modeling, secure architecture design, vulnerability types, and the software development lifecycle. Secure coding also requires consistency, clear documentation, and cross-team communication to ensure that security remains embedded throughout the process. One of the most critical areas in secure coding is input validation. Analysts must ensure that all user-supplied data is thoroughly validated and sanitized before it is processed. This means checking for appropriate data types, length constraints, expected characters, and rejecting anything that does not conform. Failure to validate input can lead to injection vulnerabilities, including command injection, cross-site scripting, and buffer overflows. Input validation should be performed on both client and server sides, with server-side validation serving as the final enforcement mechanism. Parameterized queries, also known as prepared statements, are a powerful defense against SQL injection attacks. Instead of constructing SQL queries using concatenated strings, which can be manipulated by attackers, developers use placeholders and bind variables that prevent input from being executed as code. Analysts reviewing application code or performing penetration testing should check for dynamic query construction and advocate for parameterization to prevent attackers from inserting malicious SQL commands. Output encoding is equally important when presenting user-generated data back to clients or storing it in logs. Cross-site scripting attacks often occur when untrusted input is reflected in a web page without proper encoding. Encoding ensures that special characters are not interpreted by the browser as executable code. Analysts must assess whether web applications are properly encoding dynamic content based on context, HTML, JavaScript URL, or CSS, and validate that all data outputs are sanitized against injection risks. Authentication and session management are core components of secure applications. Analysts evaluate whether authentication mechanisms enforce strong credential requirements, support multi-factor authentication, and protect against brute force attacks. Secure session management includes using random, unpredictable session tokens, marking cookies as secure and HTTP only, setting appropriate session expiration times, and implementing session invalidation on logout. Analysts verify that applications use secure communication protocols and never expose session IDs in URLs or logs. Password management must be handled with exceptional care. Analysts ensure that password storage mechanisms use strong, one-way hashing algorithms such as bcrypt, argon2, or script. These algorithms include salting and key stretching to make brute force attacks computationally expensive. Passwords should never be stored in plain text or using outdated hashes like MD5 or SHA-1. Analysts also verify that password reset workflows are secure, avoid secret questions, and use time-limited single-use tokens sent via secure channels. Error handling is another area where insecure practices can expose sensitive information. Developers often leave verbose error messages enabled during development, which can reveal stack traces, database queries, or internal logic. In production, error messages should be generic, user-friendly, and provide no technical details. Detailed error information should be logged securely for analyst review, but not exposed to end users. Analysts routinely test for information disclosure through error responses and flag any instances where sensitive data is revealed. Cryptographic practices must follow established standards and avoid custom implementations. Analysts confirm that applications use modern algorithms such as AES-256 for encryption, RSA or ECC for key exchange, and SHA-2 for hashing. Deprecated algorithms and protocols like DES, RC4, and SSL must be eliminated. Key management is equally important. Keys should be stored securely using hardware security modules or encrypted containers, and access should be limited to authorized components. Analysts validate that cryptographic functions are implemented correctly and not exposed to unnecessary risk. Secure code reviews are essential to proactive vulnerability identification. Analysts participate in or lead code reviews using a combination of manual inspection and automated static analysis tools. These reviews focus on logic flaws, insecure data handling, poor input validation, and misuse of security libraries. Secure code reviews help detect issues before they reach production, making them one of the most cost-effective security measures in the development process. Analysts provide clear, actionable feedback and ensure that recommendations are aligned with policy and secure coding standards. Finally, organizations must maintain comprehensive secure coding documentation. This includes internal guidelines, coding standards, examples of secure and insecure practices, and lists of approved libraries and tools. Analysts contribute to this documentation and help ensure that it is kept up to date based on emerging threats and lessons learned from security incidents. Good documentation promotes consistency across teams, reduces confusion, and supports training efforts. Secure coding should not be a collection of tribal knowledge. It should be a shared, accessible, and enforceable set of practices. For more cyber-related content and books, please check out cyberauthor.me. Also, there are more security courses on cybersecurity and more at baremetalcyber.com. To implement secure coding practices effectively, organizations must apply the principle of least privilege throughout their application logic. Analysts evaluate whether applications restrict user access based on minimum required permissions. This principle minimizes the impact of compromised credentials and limits the reach of privilege escalation attacks. For instance, an authenticated user should only be able to view or modify data explicitly authorized for their role. When applications fail to enforce these boundaries, attackers can gain access to sensitive data or administrative functions. Enforcing least privilege reduces the blast radius of potential compromises and is a foundational security principle. Secure exception handling is another critical area. Applications inevitably encounter unexpected conditions, network failures, data corruption, malformed input, but they must handle these gracefully without disclosing internal workings. Analysts look for scenarios where unhandled exceptions lead to stack traces or system messages being displayed to users. These disclosures may reveal database structures, exceeds paths, or error-prone logic. Secure exception handling means catching errors appropriately, returning generic messages to users, and logging full details securely for forensic analysis. This approach protects sensitive information while enabling security teams to investigate incidents effectively. Managing third-party libraries securely is vital in modern development. Applications often rely on open source or commercial components to reduce development time and enhance functionality. However, these dependencies introduce risks if not properly maintained. Analysts ensure that development teams maintain an inventory of dependencies, monitor for published vulnerabilities, and apply updates promptly. Tools like software composition analysis platforms automate this monitoring and can block builds that include vulnerable packages. Verifying the integrity of third-party code and limiting the use of outdated libraries are essential practices for reducing supply chain risk. Secure defaults simplify secure deployment. Analysts examine whether applications are configured out of the box to enforce security. This includes disabling debug modes, restricting administrative interfaces, enforcing HTTPS, setting secure cookie flags, and limiting default principles. Secure by default principles ensure that applications remain secure even when deployed by non-expert users. Insecure default settings create opportunities for attackers to compromise systems, especially when deployed in fast-paced development environments. Analysts advocate for configurations that require minimal changes to achieve compliance with security standards. Beyond secure defaults, analysts ensure that secure configurations are actively enforced during and after deployment. Configuration management tools help apply consistent settings across environments, including enabling secure protocols like TLS 1.2 or higher, enforcing strong cipher suites, disabling unnecessary ports and services, and locking down file and directory permissions. These controls must be documented, versioned, and reviewed regularly. Analysts test whether these configurations align with industry frameworks and internal benchmarks, correcting drift where found. Modern secure development workflows leverage automation to embed security early in the software lifecycle. Analysts support the integration of security tools into continuous integration and continuous deployment pipelines. These tools include static code analyzers, secret scanning tools, and configuration compliance checks. Automating these scans provides real-time feedback to developers and prevents insecure code from reaching production. Security gates can be added to pipelines to block deployments until identified issues are resolved, promoting a shift-left security culture where problems are identified and addressed earlier. Patch management plays a significant role in secure coding and application maintenance. Analysts ensure that development environments and production systems receive regular updates for their programming languages, frameworks, runtime libraries, and operating systems. Vulnerabilities in the platform stack can undermine even well-written code. Maintaining up-to-date software eliminates known flaws and strengthens the foundation on which applications operate. Analysts collaborate with developers and system administrators to ensure update schedules are aligned with security priorities. Security testing must be continuous and comprehensive. Analysts support and participate in multiple layers of testing, including static application security testing, SAST, dynamic application security testing, DAST, and interactive application security testing, IAST. Penetration testing remains a vital component, simulating real-world attack scenarios to identify complex, contextual vulnerabilities that automated tools may miss. Regular testing ensures that security remains a constant focus throughout the development lifecycle and that previously unknown issues are detected and resolved. Fostering a culture of security awareness is essential. Analysts work alongside development leads to provide secure coding workshops, threat modeling sessions, and updates on emerging vulnerability trends. Teams that understand the why behind secure practices are more likely to adopt them consistently. Analysts serve as educators, helping technical teams internalize security concepts and empowering them to take responsibility for the security of the code they produce. A strong security culture improves collaboration, reduces resistance to controls, and supports sustainable security outcomes. Lastly, secure coding practices must evolve through continuous improvement. Analysts lead retrospectives following security incidents or audit findings to evaluate what coding practices may have contributed to the issue. They incorporate lessons learned into updated coding standards, refine automated tool configurations, and document new secure patterns. They also track industry developments to stay ahead of new vulnerability classes, supply chain risks, and secure coding technique. By viewing secure coding as an evolving discipline, organizations build long-term resilience and adaptability into their software development practices. To conclude, Episode 1-2, Secure Coding is far more than a development task. It is a collaborative effort that spans security, development, operations, and compliance. From validating inputs and managing credentials securely to automating security checks and updating documentation, every step contributes to the overall strength of an application's defense posture. Analysts play a key role in championing secure coding, identifying weaknesses early, educating teams, and enforcing standards. Mastering these practices will serve you well on the CYSA Plus exam and prepare you to guide secure software development in any modern enterprise. Thanks for listening. To learn more about cybersecurity, please visit baremetalcyber.com. There you will find best-selling books, videos, and even more free cybersecurity training courses. Please subscribe to the Prepcast and our various podcasts. And thanks for listening.